Hello, this is Dr. Julie Whitney, and in this video I will continue my discussion of how the design cycle looks when you're an engineer in industry, with an example from my time at Lexmark here in Lexington. Lexmark at that time made inkjet and laser printers for big companies as well as consumers. The products I was working on were color laser printers. This is an example of one of the printers I worked on. Remember that I told you it's very common to work on just a subsection of a complex product. Well, a color laser printer is a very complex product. The way it works is that the printer gets a digital file from your computer or from a scanner, a whole device onto itself, and then the digital file magically gets changed into laser pulses that change the charge on a photoconductor drum. And the lack of charge then attracts or repels charged toner onto its surface. That part is also super complicated. Then the color laser printer takes that and does it for black and cyan, which is kind of a blue, and a yellow and a magenta, which is kind of a pink color. Those are the three primary colors in printing. Now those need to be pulled down onto a special plastic tube called a transfer belt, and they pull it down by the use of electrostatic forces, and then they collect those in sort of an aligned stack. Then the toner's pulled from that belt onto a piece of paper using another electrostatic field. Now that was a subsection I worked on. Finally, the paper with the toner stuck onto it went through a fuser, another complicated piece, and that heated up the toner and permanently melted it onto the piece of paper. In addition to those major components, it also took engineers working on the science of picking paper from a stack, engineers for the motors that we used. Some did sound or electromagnetic waves that the system gave off. Some people did the control panel, and on and on. So let me show you the part that I'm talking about. This is one of the color laser printers we worked on. This is the Lexmark CX310. C stood for color, and it's a color laser printer meant for small, medium work groups. So it's not one of the big monsters that we worked with. I'm going to show you where the part was inside the printer that I worked on. So in order to get to that part, first I have to open it up so you can get to the color cartridges. But I didn't work on the color toner, that was a different part. I can open it up this way, and down here you can kind of see the part, and I'll show it to you in a moment in a close-up, but that's not really where you can see it best. To get to the part that we did, you need to take off this cover right here. And this is the waste toner box. You need to take that off. These are the photoconductors right there, and the developer rolls, they put the toner onto the photoconductors. The photoconductors themselves put the toner onto this piece right in here. This is the transfer belt. Right there, and that was the part that I worked with. The transfer belt right in there, it's a black, that's that black shiny piece, comes around here, and in the front, this is the second transfer area. This roll right here is the second transfer roll, and there's a wide nip is right underneath that. So that is the printer that we worked with. The problem. The problem we had was that when a stack of toner that we needed to get from the belt to the paper was really thick, it was hard to get enough of an electrostatic field to pull it over. We could increase the power, but pretty quickly the field was such that we would get these tiny lightning bolts inside the toner, which would discharge it, and discharged toner does not go where you want it to. As the printers we were required to go faster, the problem just got worse. All of our competitors were having the same issue. The race was on to find an inexpensive solution. We were developing a printer for large corporations that was the fastest yet, and the print quality was what we called across the room ugly, meaning that you could see it was bad if someone held up a page and you looked at it from across the room. That was unacceptable. The key to this design challenge was understanding exactly what was going wrong and why. and this process took about a year. It started with a model that I inherited when I first moved into color laser development. The model had been created by one of the senior technical people at Lexmark, but since he didn't work in our subsection, once he created it and handed it off, nothing happened with it. It was written in Fortran, an old programming language that I'd studied 20 years earlier when I was in college. Note that eventually members of my team migrated it to MATLAB, which you're studying it, so that they could use it too. I took the model and spent some time learning how it worked and what it was telling me. I was eventually able to demonstrate that it predicted some basic things about this problem, that I could use it to predict about when our printer would show the problem, but not why. And so it was part of the answer to understanding what the problem was. The second clue came from lots of lab testing. We had a system that could be used to check the charge on the toner, and I made a long-term study out of what the charge on the toner was as it went through our system. I learned that right after each color toner was placed on the transfer belt, that as it was leaving that area, suddenly it increased in charge. I found that we were creating a small corona right after each nip and charging the toner on our transfer belt that way. The third part of the discovery was learning how electrostatic fields would build in a piece of paper and how different papers built them differently. We found that when you tried to build the electrostatic field quickly, when you were printing fast, the paper would tend to create the little lightning bolts. We found that what we needed to do was slow down that whole process. We needed to build that field more slowly in the paper, even though we were trying to print faster. The solution was to move to what we called a wide nip. We used two rolls behind the paper and controlled the voltage on both of them so that the field would build more slowly. The wider nip meant we had more time even when we were going faster. This allowed the fields to build without the lightning bolts, and the print quality dramatically improved. We applied for patents and rushed to push this into our printer that's already under development and headed out the door. I want to point out that I use the word we a lot in this story, even though it was me that figured out what was going on and me that played with the model and did the testing. In the end, it was my team working with me that made this a real design for a real product. The wide nip was a huge success. All color laser printers that Lexmark make to this day have that wide second transfer nip. In conclusion, the design process for those of you who choose to work in industry is frequently focused on the prototype and test portion of the design cycle that you have studied. It's fast-paced, and good engineers will work hard to understand the key physics that will determine if your design can get to that next level of performance. In doing so, there'll be lots of designs that don't work. You are on the bleeding edge after all, and you will analyze and try to understand why. You will develop experiments and models to tease out what's hiding in there and then push that new knowledge into your designs. In the end, you will become perhaps the world's expert for a while on a particular part of a particular product. For me, it was fun, never boring, although frequently challenging, and very satisfying when you finally figured out how and why something was working the way it was.